So this is Chemistry 108 at York College. Today is April 14th, 2015, and we are continuing on Chapter 6. So, as I'm sure you all remember, the last thing that we were doing was looking at the combination of reactions. Right, and so here's a visual and how quantities like delta G, which are state functions, can be derived as the sum of their parts, right, or as the sum of the delta H's for reactions that somehow can combine to make one final reaction. So here's kind of a graphical or a visual way to look at it. So we have graphite plus oxygen, right, being converted to CO2. We saw that example, in one of the slides way back. And the delta H for that is negative 393.5 kilojoules, or actually kilojoules per mole. If we go directly from the graphite and the O2 to CO2, you can get this big long red arrow here. Now, it's also possible to do this reaction in steps. And for example, you go from graphite to carbon monoxide plus oxygen, and then you go from carbon monoxide plus oxygen to carbon dioxide. If you go directly, or you go in steps, the sum of the delta H's is the same, right? So the sum of the C plus O2 to CO plus half O2, negative 110.5, plus negative 283.0, all the way down to CO2, that sum equals exactly the negative 393.5. Right, and so if we were going to look at it the way we did at the end of the last class, we'd look at these two reactions. Right, so the first reaction goes something like this. Graphite plus half O2 gives you carbon monoxide. Right, then carbon monoxide plus another half O2 gives you carbon dioxide. And what cancels here? Well, whatever is the same on the left and on the right is going to cancel. So what's going to cancel? CO is going to cancel. The half O2 is not going to cancel because they're both on the left. Instead of canceling, what they're going to do is they're going to add. So a half O2 plus a half O2 equals a whole O2, or one O2. And so you get C plus O2 gives you CO2. Right? And so these two kind of fractional or pieces of the reaction add up to the whole reaction, both in terms of the reactants and products and in terms of the delta H. Okay, so here is one that is kind of, if you can do this, you can do anything, any problem of this sort. Remember, what happens when you reverse a reaction? What happens to delta H? It becomes the sign changes, right? It becomes negative, or if it's negative, it becomes positive. What happens when you, say, double a reaction? Yeah. And if you add or subtract reactions, if you add the reactions, they add, right? The delta H's add. So put your heads together gently and shake the spring break out of your neighbor, and let's give this one a try. So before you go, we actually go and give this a try. We're going to have to remember, what is the standard enthalpy of formation? What is that referring to? That's referring to a particular reaction. Remember what standard enthalpy of formation of anything is? No? Yes? It's the enthalpy associated with the formation of a compound from its elements, right, in simplest form. Delta HF, remember delta HF? It's in there somewhere. So the enthalpy of formation refers to the formation of a compound, in this case CS2, from its elements. So it's going to be something plus something gives me CS2. and in this case it's liquid. So how could you form CS2 from its elements? C, in this place graphite, because there's more than one solid form of C, plus S, rhombic. And these are just different states. Remember, solid carbon comes in at least these two flavors, right, diamond and graphite. So we don't just write an S, we have to write specifically what it is. Same thing with sulfur. There's different forms of solid sulfur, so rhombic is the most stable one. So C plus S gives me CS2, and there's one more thing I need to do. Balance it. 2. So this is what you're aiming at using those. Go for it. Let's do some work. Let's do some work together. When I look at this problem, what I see is, okay, so I want to get here. I want to get to C plus 2S gives me CS2. And one of the equations has a C, and one of the equations has an S, and one of them has a CS2. They're not all necessarily in the right proportions or in the right place yet, but they're all there. And so in order to get from those three equations to this one down here, the way I'm looking at it is I need to get my C in the right place, I need to get my S in the right place, and I need to get my CS2 in the right place. And I need to get them in the right proportions, and hopefully when I do that, everything else is going to cancel. So the first reaction has C plus O2 gives me CO2. I don't know about the O2, it's not here. I don't know about the CO2, it's not here, but the C is in the right place. Right? The C is a reactant. Now the second one, the S is in the right place. It's also a reactant. But here I have 2S, there I have 1S. Right? So what do I want to do to get from 1S to 2S? I want to double it. So I'm going to write the first one first, C graphite plus O2 gas gives me CO2 gas, and delta H naught of reaction equals negative 393.5 kilojoules per mole. I'm just going to leave that the way it is. The second one, I'm going to double, right? So I'm going to get to 2S rhombic plus what? 2O2 gives me 2SO2. And the delta H is double 2 times negative 296.1, which is going to be equal negative 592.2, I think. And then for the third reaction, I've got my CS2. I need CS2, but it's in the wrong place. Right? In the final reaction, it's a product. Here, it's a reactant. So what do I do when I have the reactants and products mixed up? I'm going to reverse the reaction. So I'm going to get CO2, and if you're paying attention, you're going to see the magic happen now. Right? CO2 gas plus 2SO2 gas gives me CS2 liquid plus 3O2 gas. And now delta H is, change the sign. Same number, change the sign. Positive 1072 kilojoules per mole. So what's going to happen? I'm going to add this all together. And look at this. The CO2 and the CO2 cancel. The SO2, 2SO2 and 2SO2 cancel. 1 plus 2 is 3. 3 O2s and 3 O2s cancel. What's left? C, graphite, plus 2S, rhombic, gives me CS2, liquid. And the delta H is just going to be the sum of these three. And somebody got it, I think. What did you get? 80 something? 80 positive? 83? 86? 0.3. Actually, we're going to look at just decimal places, right? So positive 86 kilojoules per mole. Can I help you, sir? Oh, thank you. Questions? So this is an example of what we would call Hess's law, by which different reactions, sort of the state functions associated with them, such as delta H, will add together when you add the reactions. Okay, okay, that's all there. Okay, it's what we did. Can we do another one? Yes, so we're going to take a look at this. This is a little bit interesting here, right? So here, don't look at that, because that's the answer. But well, here's actually quite a simple. Well, let's look at this. Let's look at this. Here's quite a simpler one in terms of the mathematics, but the concept is a little more difficult. Right here, we've got. Remember solutions, right? So when you put an ionic compound into solution, what do? You add water, aqueous solution. You add water, and then the positive ions and the negative ions break apart, right? They dissociate and they ionize. And the water kind of goes, they kind of intersperse throughout the water. So this process down here you could think about as the solution process, right? The first thing you have is a sodium chloride crystal or something, solid sodium chloride. And then when you solvate them, you have positive ions, negative ions, and they're surrounded by water. Right? If you think about what conceptually is happening, it's not exactly what's happening when you pour the water in, but it doesn't matter because it's a state function and the pathway doesn't matter. Right? You could, if you had the means to do so, first pull the positive and negative ions apart. Right? Here, the positive and negative ions are apart. And there's water surrounding the ions. What if we first pulled them apart, and so you have the ions apart with no water around them, and then in a second step added the water? Right? That's kind of another illustration of how delta H is a state function. So when you go from here to here, there's a delta H associated with that. It's positive 4. When you go from here to here to here, there's a delta H associated with each step. So to go from this stage to this stage, you might imagine that requires a whole bunch of energy, right? Because the positive and negatives like to be next to each other. And so in order to get them apart, you need to add a whole bunch of energy. And so the heat here is quite high. It's 788 kilojoules per mole. Then, once you get from the gaseous ions to the hydrated ions, the delta H of this process is negative 784. So you have positive 788, negative 784. You add those together, you get 4, which is this. As for doing another problem, we'll look one up during the break, and we'll do one. But right now, these are hard to make up on the fly. Okay. The last concept, I think this is the last concept that we're going to cover in Chapter 6 is called specific heat. And so the specific heat of a substance is the amount of heat, and there's some terminology here that we need to know that's kind of, well, specific. Right, the specific heat of a substance is the amount of heat required to raise a temperature of 1 gram of a substance by 1 degrees Celsius, or by 1 Kelvin. And who's done the coffee cup lab? Anyone's done the coffee cup lab yet? Okay. The styrofoam cup, yeah. Yeah. So that's, if you've done that, then you've seen this already, right? So the specific heat is the amount of heat that raises the temperature 1 gram of a substance by 1 degree Celsius. And so, you know, your book has a table of different specific heats, right? The unit on specific heat is joules per gram degree Celsius. So joules is in the numerator, and both grams and degrees Celsius are in the denominator, right? Because it's the amount of heat in joules per divided by 1 gram, grams, and 1 degree Celsius, degrees Celsius. So you'll notice that water, you know, here's some very common substances. You'll notice that water has a very high specific heat relative to many other substances. And this is why you go to the beach in the summer, and it's a little bit cooler, right? Because it's by the water. The water heats up slower than the land.
Do we have to memorize the table?
No, you do not. But again, if you're doing it right, by the time you take your test, you'll probably have memorized the one for water. But no, they will be provided for you, or you will have the information necessary to calculate on your own. Heat capacity is a quantity similar to specific heat, or related to specific heat. And it's the amount of heat required to raise the temperature of a given quantity of the substance by 1 degree Celsius, right? And so the specific heat is a specific example of the heat capacity where the quantity is 1 gram. And to make it even more confusing, in a lot of places you'll find people talking about the specific heat capacity when they really mean the thing on top, S. And so C equals M times S, right? So S is per 1 gram, M is for many grams, right? So if you have 5 grams, you multiply 5 by S to get you C. Okay, so here is the formula that tells you just about everything that you need to know for the rest of this chapter, give or take a little bit. It's Q equals ms delta T. Right here it's M times S times delta T. Very often you'll just see Q equals ms delta T. And if you're at constant pressure, what's Q? What? Well, Q is heat, right? And there's a quantity that we've been looking at quite a bit recently that has something to do with heat at constant pressure, which is enthalpy, right? Delta H is at constant pressure equals Q at constant P equals ms delta T, right? So here's a note. Negative, yeah, so yeah, this is delta H. Yeah, so delta H in terms of, not in terms of joules per mole, just in terms of joules, right? So if we're looking at a reaction or something, then yeah, it would be joules per mole. If we're just looking at something where we don't know how much of something is, it would just be joules. So the delta T, remember, is always final minus initial. Keep this in your mind, because remember, in thermochemistry, the sign means you have to keep track of the sign, right? The sign tells you whether heat's going in or heat's going out. It makes a big difference. Okay, so using that equation, right? So here's a guy working with iron bar. How much heat is given off when an iron bar of 869 grams cools from 94 Celsius to 5 Celsius? S is the specific heat, and that's the number you asked if we're going to have to memorize them or not. And the answer is no, and the answer is I don't know what it is for iron right off the top of my head, so I'm going to flip back one slide and check. And for iron, Fe, the specific heat is 0.444 joules per gram degree Celsius. So S for iron metal, right, S equals 0.444 grams per, no, joules per gram degree Celsius. You may find it in some places joules per gram times Kelvin, right, because they're essentially the same thing. So S equals 0.0444 joules per gram degree Celsius. How are we going to do this, right? So Q equals M times S times delta T. What's M? Yeah, that's the mass, 869 grams. S is 0.444 joules per gram degree Celsius. And what's delta T? We need to do final minus the initial. So it's going to be 5 minus 94, which is going to, in fact, be negative 89 when we do it out. Right? So that's going to be the grams and the grams cancel, the degrees Celsius and the degrees Celsius cancel. And what we're left with is joules. And I think this is all here. And so I think I have the math here. So because this is 89, right, this is going to be negative 89. When we do it out, you know what, let's write this out anyway. So 869 grams positive, 0.444 joules per gram degree Celsius. It's positive, right? Mass is basically always going to be positive, right? It's very hard to get a negative mass. I guess you could take stuff away, but mass is positive if you have an actual thing there. The delta, the S is always going to be positive. And so what's negative here? Negative here is, what's here is negative because the temperature is going down. And when we put that together, we're going to get negative 3.4, right? We're limited by two significant figures, times 10 to the negative, no, 10 to the positive fourth joules. What does a negative sign mean when we're talking about Q, when we're talking about heat? If we're thinking about like Q plus W, for example, Q being negative means heat is going into or out of the system. So yes, it means exothermic, right? So heat is going out. Does this make sense? Yes, heat is going out. The system, the iron bar, is going from 869. It's going from 94 to 5. Okay, so this is, if you haven't done it yet, a rough approximation of what you do in your lab, in the coffee cup lab or the styrofoam cup lab. This is what's called a constant pressure calorimeter. And you're correct. So delta H divided by, Q divided by N is going to give you delta H. You're correct about that. So in a constant pressure calorimeter, you basically have a cup, styrofoam cup, or something that holds the heat. But even though this is capped, it's not a tight seal, right? It's not going to like explode. It has air can get in and out. So the pressure is constant and it equals atmospheric pressure. And then you're going to have some kind of, in practice, you're going to have to be able to stir so you can make sure the whole, the top of the cup is the same temperature as the bottom of the cup, right? And you're going to have a thermometer to monitor the temperature. And then you're going to have something going on in the cup. And what are you measuring ordinarily with a constant with a calorimeter? What are you observing? temperature, or actually more specifically the change in temperature. Right? Before the reaction it's one temperature, after the reaction it's a second temperature, and you get the delta T. And so the Q of the system equals the Q of the water plus the Q of the calorimeter plus the Q of the reaction. Now, sometimes for simplicity's sake, and we'll mention this, we'll say the calorimeter itself doesn't really matter. The cup doesn't, in other words, that's saying the cup doesn't change temperature very substantially. But for now, we'll leave it in. It's the Q of the system equals Q of water plus Q of the calorimeter plus Q of the reaction. Sorry?
There's water in there?
Yeah, so this is, well, it's your reaction mixture, which generally is going to be in aqueous solution or in water. It doesn't have to be water, it could be something else, but ordinarily we'll use water. The point of the styrofoam cup is that no heat, at least on the time scale that we're looking at things, no heat goes in or out. Right? Of course, we know if you have a styrofoam cup and you leave it out for a few hours, it's going to cool down. But if you leave it out for a minute, it's not going to cool down much. Right? And so if you do your reactions very quickly, for all intents and purposes, no heat enters or leaves. So what kind of system is this? Is it an open system, a closed system, or an isolated system? Who thinks it's open? Who thinks it's closed? Who thinks it's isolated? It's so who wants to justify their choice? Sure. Go ahead.
It's a closed system because no heat enters or leaves.
So what's the definition of a closed system?
Closed system is when the temperature remains constant inside and like it's not being transferred in and out.
Not necessarily the temperature. There's no heat that's transferred in or out of the system. Well, I guess so yeah, there's no heat transferred. So yes, you're right. The overall, well, it's a little complicated, but yes, there's no heat that goes in and out. Right? Components can change in temperature, right? Different parts. But that's the same as an isolated system, right? In an isolated system, no heat goes in and out. Why is this closed or isolated, depending on what it is? Why did you say it's closed?
That was my reason.
Go ahead.
I said it's isolated because it remains a constant pressure.
The pressure, I think you're getting something a little mixed up. So in an isolated system, there's no exchange of heat and there's no exchange of matter. Right? Whereas in a closed system, there's no exchange of heat, but there can be exchange of matter. So because this is not a really tight seal, right, stuff can go in, stuff can go out. We can add something to it, we can add reactant to it, and so on. So, but the important part is this, right? The important part is no heat enters or leaves. And so if no heat enters or leaves, what's Q of the system? Sorry?
Like heat goes in or out?
But if no heat goes in, yeah, that's what it means. But if no heat enters or leaves, then what's the value of Q? 0. Right? So this whole thing, if it's really that, is 0. So what do we get? We get the Q of the reaction. This whole thing equals 0. So in order for it to add up to 0, this has to be the same as the negative of this. Right? Like positive 5 and plus negative 5 equals 0. So Q of the reaction equals a negative of the Q of the water plus the Q of the calorimeter. So the Q of the water equals ms delta T for the water. Q of the calorimeter equals the C of the calorimeter, or the ms of the calorimeter times delta T. And when you put that together, if the reaction is at constant P, right? If you put that together, this plus this is the negative of that. And again, delta H, if we're thinking about per moles, then we would take Q divided by the moles of the reaction. Okay, so let's let's think about this, okay? Let's say in our coffee cup calorimeter, there's also, we're not going to do problems with this, there's also what's called constant volume calorimetry, also known as bomb calorimetry. And it's a little more complicated, so we don't do the calculations. But in bomb calorimetry, you have basically a actually, it's the opposite of what you think about as a bomb, right? You have a device that is basically something like stainless steel, really heavy and shuts really tight, right? So what does that mean? That means it's resistant, it's not going to blow up, right? So if you burn something, ordinarily if you put it in a balloon or something, the balloon would blow up or the coffee cup would blow up. But if you do that in a constant volume calorimeter, in a bomb calorimeter, what's going to happen is the pressure is going to increase, right? Because the volume doesn't change. And you can also do calorimetry with that. It's, like I said, it's a little more complicated. If you're interested in bomb calorimetry, become a chemistry major, and you do that in Chem 421. But back to here, right? Let's say we have our coffee cup, right? And we have our thermometer, and let's assume QCal equals 0, right? So the calorimeter itself doesn't change. And so we put a bar of iron, right? So the bar of iron is not going to be quite so big. But let's say the bar of iron is 25-gram bar of iron. At 110 degrees Celsius. And then you put it into the water, right? Put into water in the calorimeter. The water is initially at, you know what, let's not do, yeah, let's do this. Okay, is initially at 21 degrees Celsius. You know, let's not do this one first, because the math here is going to be harder. 25 grams bar of an unknown metal. The water is initially at 21 degrees Celsius and rises after you add the metal to 52 degrees Celsius. Find the heat capacity of the unknown metal. So let's think about this, right? We've got a closed system. Closed system that is comprised of two items, or basically two things. One of them is the iron bar, and the other one is the water. Because it's a closed system, Q is 0, right? So Q of the system equals 0 equals Q of the water plus Q of the iron. And we're saying QCal equals 0. Oh, metal, sorry. Plus QCal. And QCal we're saying is equal to 0. We're ignoring the QCal and saying that that doesn't change very much at all. How can using what we already know, how can we solve this problem? Well, what's Q of the water?
4.184.
The formula is on the board somewhere. Q equals ms delta T. Very good. So Q of the water equals the mass of the water times S of the water times delta T of the water. What's the Q of the metal? Equals the mass of the metal times the S of the metal times the delta T of the metal. So if we want, we can take this and rearrange it to say Q of water equals negative Q of the metal. And if we plug in, we can say ms delta T for water equals negative ms delta T for the metal. Yeah.
So you're saying that Q system and Q cal are 0?
Yeah, so Q system in these cases is always going to be 0, right? Because it's a closed system. Heat doesn't go in and go out. Q cal is 0 because we're just taking a shortcut. We're being a little lazy. And we're assuming that the calorimeter itself doesn't make a huge difference. And so one thing I'm going to need to give you is the mass of the water. So I'm going to say we have 750 grams of water. So before we even plug anything in or do any calculations, let's think about this. What is this really saying? This is saying whatever heat is being gained by the water, that amount of heat is that same amount of heat is being lost by the metal. Or the metal, which is in this case very hot, is releasing heat, and all the heat that's being released is going into making the water hotter. This is what this is saying in English. Once we understand that what it's saying in English, then we can then the math becomes kind of a little more interesting, right? So M is, in this case, 750 grams, and S is 4.184 joules per gram degree Celsius for water, right? That's the one I said if you're doing it right by the end of this, by the time you take the test, you'll have this in your head. And what's delta T for water? Sorry? No. No. It's delta. Delta is T final minus T initial. So what's T final? Oh, yeah, you're right, yeah. 52 minus 21. Sorry about that. Which gives you 31, right? Final minus initial. That's why I was getting confused. And that equals negative, don't lose your negative, M, which is 25 grams, S, which is, we don't know, and delta T is, what's delta T for metal? Let's do the subtraction out. What is the final? The final is, the final is 52. Because if you've done your lab, when is the reaction done? The reaction is done when the temperature stops changing. When temperature stops changing, what happened? The bar and the water are at the same temperature. right? So the final temperature is going to be the same. So that it's going to be final minus initial, which is 110, right? 110. And so if we plug this in, we're going to get, this becomes 31. This becomes negative 58, right? And so now it's just a matter of doing some math. And so we're going to get calculator. 750 times 4.184 times 31. And I'm getting, I've lost my chalk. Okay, 97,278, which is really going to be two significant figures. So 9.7 times 10 to the 4 joules. That's what I get on this side. Equals, that's not the final answer, equals 25 times 58 negative. And it's negative, so it's going to be positive. So it's going to be 1.5 times 10 to the 3rd joules times S. No, not joules. That's not joules. I'm lying to you. So S is, yes, so S is joules times grams. So S is in joules times grams degrees Celsius. So this is actually going to be grams degrees Celsius, right, times S. It's grams times degrees Celsius times S. So I got 1450. And then I rounded to two significant figures. And then, that's why you need this negative sign here. And so when you do the math, you get 6 point, I did that wrong. Divided by 1.5 E3, and I get 65 joules per gram degree Celsius. So I set this problem up kind of funny. That's a really high S, but that's okay. Yeah, so this is really just puts two things together, two concepts together, right? One is this, that in the calorimeter, whatever comes out of the reaction goes into the water. Whatever goes out of the water goes into the reaction. And Q equals ms delta T. Right? Those are the two concepts that are put together. Right? The math is a little, once you've done about 10,000, the math is going to become easy. Okay, so let's take a break. You have a question? Yeah, let's take a question first.
Can you just put negative Q equals 25 times S times negative 58?
Negative Q equals,
Like negative Q water, so
yeah.
9.7 times 10 to the 4 equals 25 times S times negative 58. Can you get the answer that way?
Yeah, I mean that's essentially the same calculation. Yeah. I think. Sorry? Yeah, we'll do some more practice problems. We'll do some more problems. No. All right. You want problems? We got problems. Okay, so here's the problem. It's actually out of your book. And so here's your constant pressure calorimeter with your thermometer. And here's water. And in the water, you have NaOH and HCl. So you have 0.0500 moles of HCl and 0.0500 moles of NaOH. In a constant pressure calorimeter, the calorimeter itself has negligible heat capacity. And the calorimeter contains 200 grams of water. The initial temperature is 22.50 degrees Celsius. Then the HCl and the NaOH react. Right? And when they react, the temperature rises to 25.86 degrees Celsius. So find two things. One is Q, and is how much heat was gained or lost by the reaction. So this is a Q of the reaction. And find delta H. And so this is a point that was made earlier. Delta H is in moles. It's generally reported as joules per mole or kilojoules per mole for the reaction. And so when you mix this and this, you're going to some heat's going to either be gained or lost. That's an absolute amount of heat. But because this is a reaction, right, you have this number of moles and this number of moles giving you some product. Then once you get Q, you're going to divide it by the number of moles that you have to get joules per mole. So this is different, but nevertheless the same. It's different because we're not doing something with a metal bar, or we're not looking at the change in the temperature of the water versus the bar. What we're looking at is a reaction. So this is kind of like the one that you do in lab, because you're looking at the change in temperature of a reaction, something that happens, a process. That's why it's different. It's the same because the way you can kind of reason about it is the same. So where are we going to start? We're going to start by saying Q of the system equals Q of the water plus Q of the reaction plus Q of the calorimeter. And the Q of the calorimeter, we're told, is negligible, equals what? Say it with some conviction. 0 equals 0. Why does it equal 0? Because it's a closed system. It's a coffee cup. No heat's going in, no heat's going out. So what's Q of the water? And so I like to do it like this. I like to do this first. Q of water equals negative Q of the reaction. And so Q of the water equals ms delta T. And the Q of the reaction, in this case, is just going to be the Q of the reaction, right? Because what are we trying to find? Q of the reaction. So we can do that also. It doesn't matter which one is negative. So if we do that, it's going to be negative ms delta T equals the Q of the reaction. Okay, so what's M? 200. 200 grams. What's S? 4.184 joules per gram degree Celsius. And what's delta T? Yeah, final minus initial. So 25.86 minus 22.50 degrees Celsius. And if we do that, it's going to give us 3.36, right? So the grams and the grams cancel out. The degrees Celsius and degrees and the degrees Celsius cancel out. And, yep. And I believe I get 2.8. Yep, so 2.8. In this case, it's going to be 2.81 if we assume these are all significant, equals 2.81 times 10 to the third joules. So that's negative. Equals Q of the reaction. So let's make that negative real big. Equals negative 2.81 times 10 to the third joules. Q equals Q of reaction. Does that make sense in terms of the sign? Well, what happened when you mixed the two things together? The temperature of the water went up. So if the temperature of the water went up, the water gained or lost heat? The water gained heat. So that means the reaction gained or lost heat? Lost. If the reaction lost heat, what's the sign of its delta H? Negative. Works. Well, it tells us, the problem tells us that the heat capacity of the calorimeter itself is negligible, right? And most likely on your exam, it will be negligible because it's one fewer step to do. Otherwise, you'd have to do another step of ms delta T for the calorimeter, right? For the actual like coffee cup plus the thermometer plus the stirring rod plus the cap, right? Which is kind of annoying. In real life, you might have to do it or show that it's negligible. Yeah.
So, Q of the reaction is not positive 2.81, it's negative.
The Q of the reaction is negative. The Q of the water is, right, the Q of the water is without the negative sign. The Q of the water would be positive because, and that makes sense because the water temperature is going up, right? So the water is gaining heat. If the water is gaining heat, it's gaining it from where? It's gaining it from the reaction. So the reaction itself is giving off heat. So it's negative. So Q of the reaction is negative. So remember, like 2 or 3 weeks ago, before spring break, I said the sign is going to be important, right? The sign means not just positive, it means something about directionality. Okay, so delta H now is going to be joules per mole. And so if it's going to be negative 2.81 times 10 to the third joules. And how many moles do we have? We're not actually adding them together. Right? It's going to be 0.05 because each reactant gives us is 0.05, 0.05, and that's going to give us 0.05 water and 0.05 sodium chloride. So it's going to be divided by 0.0500 moles. And when we do that out, we're going to get negative 56.2, or negative 5.62 times 10 to the 4th joules per mole, or negative 56.2 kilojoules per mole. Okay, so do you want to do another calorimetry problem, or do you want to do another Hess's law problem with the? Well, we only have about 15 minutes, so it's gonna. Hess's law. Okay, let's do that. Let's find a good one. Let's find you a good one. Okay. All right, so we're looking now at, let's see. CH3OH, liquid, that's methanol, rubbing alcohol, one type of rubbing alcohol, plus 3/2 of O2 gas gives you CO2 gas plus 2H2O liquid. And the delta H naught of reaction equals negative 726.4, and these are all going to be in kilojoules per mole. C of graphite, or C graphite, plus O2 gas gives you CO2 gas. And the delta H of that second reaction equals negative 393.5 kilojoules per mole. And the third one is H2 gas plus 1/2 O2 gas gives you H2O liquid. And the delta H of the reaction, delta H naught of the reaction, equals negative 285.8 kilojoules per mole. What are we calculating? We're calculating delta H naught of formation for CH3OH. So what is the formula going to be for the delta H of formation for CH3OH? Remember, what's the delta HF? It's the formation of the compound from its elements. So it's going to be C, graphite, plus, what's the most stable form of hydrogen at room temperature? H2, gas, plus, and what about oxygen? O2 gas gives you CH3OH, and what do we need to do now? In the CH3OH liquid, you need to balance it. So we're going to put in 2 H2s and 1/2 of an O2. And so let's call this reaction 1, let's call this reaction 2, let's call this reaction 3. So give it a try. Yep. Okay, so a lot of you got this. Some of you are staring kind of blankly at the page. That's okay either way, as long as eventually you get it. So when I look at this, a bunch of you tried to start with the oxygen, right? And when I look at that, I say to myself, I have no idea what to do with that oxygen, because there's 3 of them all have oxygen in them. I don't know what I'm going to have to get on the left and what I'm going to have to get on the right. So I'm just going to leave the oxygen alone and hope that magically falls out at the end. And in fact, it will, as we'll see. What I'm going to work with is, what I'm going to try to figure out is the chemical entities that are only in one equation at a time. So if I start with number 1, the CH3OH, right, is over here. Product side. Up there it's on the reactant side. So that's bad. I want to reverse it. What's good is that there's one CH3OH and one CH3OH, so I don't have to multiply it. So I just have to reverse it. So I'm going to change 1 into CO2 gas. I'm going to reverse it. Plus 2H2O liquid gives me CH3OH liquid plus 3/2 O2 gas. And what's the delta H of that? Positive, right, 726.4. And I'm just going to write kilojoules per mole for all of them. Number 2, well, that one looks okay because the C graphite is on the right side and in the right number. So I'm going to leave it. C graphite plus O2 gas gives me CO2 gas, and the delta H stays the same. And for the third one, well, the H2 is on the correct side, right? It's on the left. It's on the reactant side. But there's 1 here and 2 here. So I'm going to want to double it. So when I double it, I have to double everything. So I get 2H2 plus how many O2? 1 O2 gives me 2H2O. And the delta H for that is going to be 2 times 285.8. And what's 2 times 285.8? Negative 571.6. And that's still negative because I didn't flip it. OK, and so a lot of you that I talked to got up to here, but then, and you started canceling stuff. So the CO2 cancels with the CO2, and the 2H2O cancels with the 2H2O. And so what do you have? You have your C graphite and your 2H2 and your CH3OH, and now you got some oxygen left. And a lot of you got up to this point and said, well, what do I do with the oxygen? Well, what's 1 plus 1? 2. 2 oxygens on this side. 3/2, which is the same as 1.5 oxygens on this side. Right, so if I have 2 on this side and 1.5 on this side, what can I do? I can subtract out 1.5 from this side. That takes me to 0. And if I subtract out 1.5 on this side, and I have 2, I subtract out 1.5, what am I left with? Half. And so this comes out to 1/2 O2. And look at that, 1/2 O2. So as we hoped, and on an exam problem it's going to happen that way, the O2 magically fell out. And so we got C graphite plus 2H2 gas plus 1/2 O2 gas gives us CH3OH liquid. And all I have to do is go plus add, and I get delta H naught formation equals, what's the number, 283 or something? 2, and that's negative, right? Negative 238.7 kilojoules per mole. See you on Thursday. We're going to start chapter 7.